Hi Harriet. So get your yellow book out and let's do your retrieval roulette. So pause, answer the questions. Okay, so here's your answers for marking. Just one I want to point out to be careful of. See question 6 there. Sulfur dioxide, that's SO and then a wee small 2. Okay, so not a full size 2 like that. That's just the way Excel's showing it on me there. Okay, I think the rest of them are self-explanatory, so get those marked for me. Thank you. Okay, so last week we started looking at our new topic, which is heat. A couple of things I just want to get refreshed in our memory. So we need to make sure that we know the difference between heat and temperature. Temperature is really used to measure how hot something is, and it is measured in degrees Celsius. And heat is a form of energy, and we know from earlier on in the year that all energies are measured in joules. The direction that heat always flows in, it always goes from a hot area to a colder area. And there's a couple of different things that affect the rate of heat transfer, or how much something's going to heat up whenever you supply it with heat. So one thing is that the temperature difference is going to affect how much something's going to heat up, and the mass of the object. So the bigger the mass, the more energy that is required. Now, last day I had asked you to do page 48. I've had a look through your answers, a lot of really good answers, so I'm just going to go over this nice and quickly. So question 1, we had to fill in the blanks. The time it takes to heat some water depends on the mass of water you're heating and the temperature that you want the water to reach. It takes a longer time to heat a greater mass of water because it needs more energy. It would also need more energy to heat the same mass to a higher temperature. Then we had to explain why all of these different things, and yours does not have to be worded exactly the same as mine, as long as the key message is the same. So explain why it takes longer to heat a cinema to the same temperature as a house. There's much more mass to heat in a cinema. So like there's much more air particles. And then explain why it takes longer to boil a pan of water than to heat a pan of water to 50 degrees Celsius. So the boiling pan must be heated to higher temperature, so that's going to require much more energy. This here, we want a good one. I like this question. Rewrite this sentence so that it is correct. So the sentence was, the energy stored in the sun is 6 million degrees Celsius. Now, energy is measured in joules and temperature is measured in degrees Celsius, so those two things do not go together. So I have rewritten it as the temperature of the sun is 6 million degrees Celsius. Sneaky one that, isn't it? Okay, question 3 was picking which one of these that the statement applied to. So measured in joules is energy, measured with a thermometer, temperature. Doesn't depend on how much material there is, temperature, but I think this is a wee bit of a funny one, it depends how you read it. Measured in degrees Celsius, temperature, and increases if you heat something for longer, both of them. Question 4. It takes 4,200 joules to raise the temperature of 1 kilogram of water by 1 degree C. How much energy in kilojoules? Don't know why they changed the units on it, just to be evil. Would it take to raise the temperature of 1 kilogram, so the same mass of water, by 2 degrees Celsius, so double the change in temperature. So because of that, I've taken my 4.2 kilojoules and multiplied it by 2 to get 8.4 kilojoules. And then for B, how much energy in kilojoules would it take to raise the temperature of 3 kilograms? So we've got 3 times the mass now by 1 degree, but the temperature change is the same. So that means I was able to take this 4,200 joules or 4.2 kilojoules and multiply it by 3 because we've got 3 times the mass. And that got me 12.6 kilojoules. Okay, so over on page 49 is a little experiment. We're going to leave this one for now, and then just turn over for me please to page 51. Don't worry, we will go back to that one, alright? So, we're going to look and spend a fair bit of time looking at the different ways that heat energy can be transferred and the different methods that takes, and that depends really on the material and the situation that we're in. So there's 3 main methods that heat energy can be transferred by. So conduction, and if you were to ask me what's the definition of conduction, it would be, I would say that that conduction is the method of heat transfer in solids. Now I've added in a wee extra bit here about whether these require particles or not, because that can come up quite a lot in questions like, how do we know it's not conduction or such and such, okay? Convection, that's the method of heat transfer in liquids and gases. Now liquids and gases collectively are known as fluids. So if you want to add that in for me, please. And then infrared radiation, sometimes we'll just refer to this as radiation, and that's fine. It's not nuclear radiation, different infrared radiation, and that occurs in gases and in vacuums. Now, a vacuum in science is just a place where there's absolutely no particles. So if you imagine you had a wee cup full of air and you sucked all the air out of it and then there was absolutely nothing left, just no air particles or anything, that would be a vacuum. So like outer space would be a vacuum. Let's add in what that is. So it's where there is no particles, nothing whatsoever. Okay, so we're going to start off looking at conduction, and we're doing a little bit on this today. Now, this is one of my most favourite demonstrations that we ever do in school. I'm really sad I can't get to do it for you. I'm actually hoping that you will be able to do it at home, okay? So if you have ice cubes in your freezer, get 2 ice cubes out. Before you get those out, find a metal surface and a wooden surface. So if you have a wooden chopping board and a saucepan, say, then you could do this. In fact, I might be able to do this on camera for you, but you give it a go as well. I'm just going to go and get my stuff so that I can do it, okay? Okay, so I've got here just a saucepan lid, and that's obviously made out of metal, and then this is just a plastic chopping board, okay? Now, what I'm going to do is set an ice cube on each of these and have a think about how fast you think they're going to melt. Which one do you think is going to melt faster? Okay, have we think about that? Right, I've got 2 ice cubes, they're starting to melt in my hand, so I'm going to set one on the metal and one on the plastic, and let's have a wee look and see. This is exciting. So, most people think that the ice cube on the plastic will melt faster and that the ice cube on the metal will melt slower. But hopefully you can see here, look, the one on the plastic's hardly melted at all, but the one on the metal, look how much water's come off that one already. It's melting much, much faster. Okay. Well, haven't quite got a fair test here because my things are different thicknesses, but do give this a go at home as well, and you will see that the one in the metal melts much faster. I'm just going to leave them sitting there while I talk here, okay? So what's actually happening here is the heat energy is transferring, remember, always from hot to cold, okay? And the ice cube's obviously colder than the chopping board or the saucepan lid. So the heat energy is travelling from both of those things to the ice cube. And these 2 things are at the same temperature. Whenever you touch the metal, it will feel colder, but it's not, it's the same temperature. It's just that metal materials are much, much better conductors of heat energy than non-metals. So this, because it's hotter than the ice cube, is transferring the heat energy to the ice cube to melt it. This is hotter than the ice cube and it's transferring heat energy to the ice cube to melt it, but it's not as good at doing it as the metal is. So because the metal is a really, really good conductor and it transfers that heat energy really quickly, then the heat energy is going from this to our ice cube much faster than it is from the plastic one. And the plastic one, look, has hardly melted at all. There's no water on that surface, whereas this is now in a little puddle of water. Do you see that? Okay, so that's all that's happening. Because the metal is a better conductor than the plastic, the heat energy transfers much quicker, and that's why this ice cube is melting faster. So do promise me you'll give that a go at home, because it is quite cool to see. And I'm just going to leave these sitting and we'll see what they're like whenever we get to the end here. So I should have said we will learn why the metal is a better conductor just in another lesson, not today. Okay, so in our notes we have to describe what happened and explain why. I will write that in and then I'll get you to copy it in. Okay, so here's what I've put. The ice on the metal surface melted much faster than the ice on the plastic surface. This is because metal is a thermal conductor. Haven't used that word yet, I don't think. So transfers heat energy quickly. So that's the word that we give for something that transfers heat energy really, really quickly, or a solid material that transfers heat energy really quickly. It's a thermal conductor. The plastic is a thermal insulator, so heat energy transfers slowly from it. So a thermal insulator is something that is a bad thermal conductor. Now down at the bottom of page 51 here, we've got the official definitions that we'll be using for these. So thermal conductor is a material that allows thermal energy or heat energy, it's fine to say that, to transfer through it quickly. And a thermal insulator is a material that does not allow thermal energy to transfer through it quickly. It's a poor conductor of heat. Now, very important to note, it's not that it doesn't allow heat energy to transfer through it. It does happen. It just happens really, really slowly. Right, let's have a wee check in on our ice cubes. Exciting. Okay. There's the plastic. Still nothing. But look at this. Look. Isn't that cool? Okay. I'm maybe a wee bit too excited about it, but I do like it. And do give it a go at home. Okay, so this is an experiment that we can carry out to test different metals and see which ones are better conductors than other ones. Okay, so we know metals are good conductors. They do allow heat energy to travel quickly through them, but some allow the heat energy to travel quicker through it than others. Okay, so most metals are good conductors of heat, but they don't all conduct heat at the same rate. The faster a material allows heat to flow through it, the better a conductor it is. So let's look at what we have here. We've got a little trough, like a water trough, which is just basically like a container that we are going to pour water into. Now we've got these metal rods that are poking in through here, okay? And you can see what the names of them are there. We've got aluminium, brass, copper, steel and zinc. So this one's the aluminium one, this one's the brass one, etc. Now, these little rods are all exactly the same as each other, otherwise it wouldn't be a fair test, okay? So they're the exact same as each other, apart from the material they're made out of. Now, if you can see there at the end, we've got little ball bearings attached onto the end of the rods, and they're attached on there with like Vaseline or something like that. Candle wax can be used for experiments like this, but I think in this one it's like grease, so Vaseline. So what's going to happen, we're going to pour warm water in here and we're going to start a timer as soon as that happens, and we're going to time how long it takes for the ball bearing to fall off, because when the ball bearing falls off, that means that the heat energy has conducted all the way along here and melted the grease at the end, so the ball bearing falls off. So that's our way of knowing when the heat energy has conducted the whole way along the rod. Now, here's what I need you to do. I need you to watch the video. I'm going to link it here at the end, okay? I need you to watch the video on this and pause it as you're going, because there's text that comes along the bottom of the video. So pause and write out all of the text that comes up along the bottom of the video. You write it all in here. Now, then the experiment actually happens. Okay, it's Mr. Ross that has carried out this experiment for us. Now you don't have to worry about filling in the results table as the experiment is happening, because he puts all the results in a table at the end of the video. So at the end of the video you pause at that table and write that in there. Then I need you just to fill out this wee bit at the bottom. So the best conductor from this group is, you'll name the metal there, because it took either the longest time or the shortest time. Have a think about which it would be. And then the same for the worst conductor of the group. And then I need you to send me that page filled out. Okay, hopefully that's clear enough. I will link the video here, so click it, and then I'll see you next week. Bye.